Hey guys, tonight we're going to talk about clouds, but not the way you learned about them in 4th grade with cotton balls glued to construction paper. Tonight, you're going to stand in a summer field, head tilted back, staring at a single cumulus cloud that appears to be doing absolutely nothing. It's just hanging there in the blue, a white dollop of whipped cream that hasn't moved left or right or up or down for the past 3 minutes. Your neck is getting sore. The cloud doesn't care. It looks peaceful, static, like a photograph pinned to the sky. But here's the thing that's going to keep you company as you drift off tonight. That cloud isn't still at all. It's a screaming hurricane of activity wrapped in a deceptively gentle package. And if you could shrink down to the size of a water molecule and ride along, you'd experience one of the most chaotic, beautiful, and frankly exhausting journeys in all of nature. So, before you get comfortable, take a moment to like the video and subscribe, but only if you genuinely enjoy what I do here. And hey, drop a comment telling me where you're watching from and what time it is for you right now. I love knowing that someone in Oslo is falling asleep to the same words that someone in Melbourne is waking up to. It reminds me that while clouds might look motionless, the world beneath them never stops spinning. Now, dim the lights, maybe turn on a fan for that soft background hum, and let's ease into tonight's journey together. You're looking at that cloud, and your brain is doing what brains do. It's lying to you. It's taking a snapshot every few seconds and telling you nothing has changed. But zoom in, closer, past the scale of meters, past centimeters, down into the microscopic realm where water droplets live. Each droplet is about 10 to 20 micrometers across. That's roughly 1/5 the width of a human hair. Inside your frozen-looking cloud, there are approximately 1 billion of these droplets per cubic meter. Not million, billion, and every single one of them is moving. Some are rising on invisible columns of warm air at speeds that would translate to highway speeds if they were car-sized. Others are falling, pulled by gravity, but so slowly that the air resistance makes them drift like feathers. They're colliding with each other dozens of times per second, sometimes bouncing apart, sometimes sticking together in a microscopic marriage that makes them just slightly heavier, just slightly more likely to fall. The temperature inside the cloud might be 15 degrees Celsius near the bottom and 0 degrees at the top, creating convection currents that loop and spiral like the pattern in your coffee when you pour cream into it. Except this coffee is the size of a skyscraper, and the cream is made of 1 trillion tiny water spheres that couldn't care less about your perception of stillness. And that's just the water. The air itself is in constant rebellion. Parcels of atmosphere are rising, cooling, expanding. Others are sinking, warming, compressing. Invisible turbulence, the same force that rattles airplanes and makes your seatbelt light come on, is churning through the cloud's interior like a 3-dimensional blender set to puree. You can't see it because air is invisible, and because your eyes aren't fast enough, but if you could film this cloud with a camera that captured every millisecond, and then played it back at normal speed, you'd see it boiling. You'd see wisps tearing off the edges and vanishing. You'd see the bottom bulging and rippling like the surface of a drum. You'd see the whole structure breathing. But from down here, from your patch of grass with your sore neck, it looks like a painting. It looks like God hit the pause button on this one specific chunk of sky. And that illusion, that gorgeous, frustrating illusion, is what we're going to dismantle tonight. We're going to take that motionless cloud and turn it inside out, peel it apart layer by layer, until you understand that when clouds drift nowhere, they're actually doing everything. They're building raindrops from scratch. They're generating electrical fields strong enough to kill you. They're talking to other clouds. They're sculpting themselves in response to winds you can't feel. They're slowly dying while simultaneously being born at the edges. They're performing a magic trick where the illusion is stillness, and the reality is a physics problem with 10,000 moving parts. You know what's funny? The ancient Greeks thought clouds were exhaled by the earth, literal breath from the planet's lungs. The Victorians thought they were floating steam, which is closer but still misses the point. Even now, in an age where we can measure the diameter of individual droplets and track updraft velocities with Doppler radar, most people still think of clouds the way they thought of them as children, as fluffy things that float and sometimes rain. It's like thinking of the ocean as water that moves a little. Technically true, cosmically insufficient. So tonight, as your eyelids get heavy and your breathing slows, you're going to become an expert in apparent stillness. You're going to learn how something can look motionless while being utterly, violently, beautifully active. And maybe, just maybe, You'll never look at a summer sky the same way again. Every cloud will become a secret, and you'll be one of the few people on Earth who knows what's really happening inside that innocent-looking white puff. Let's start where all clouds start, with something so small you'd need a microscope to see it, and a desperate gasp of water vapour looking for somewhere to call home. The air around you right now is full of water you can't see. Even in a desert, even in winter, there are water molecules bouncing around in the space between your face and your phone screen. They're invisible because they're alone. Individual molecules doing their own thing, spaced too far apart to bend light in any meaningful way. They're vapour, and vapour is just water that hasn't made up its mind yet. It's waiting for an excuse to become something visible, something tangible, something you could point at and say, there, that's water. But here's the problem. Water vapour is terrible at making decisions on its own. If you took a sealed jar of perfectly pure air and perfectly pure water vapour and cooled it down past the point where physics says condensation should happen, nothing would happen. The water molecules would just keep bouncing around in their gaseous state, confused and supercooled, like party guests waiting for someone else to start dancing. This isn't a hypothetical. Scientists have done this experiment. You can get water vapour down to negative 40 degrees Celsius in ultra-clean conditions, and it'll just stay vapour, stubbornly refusing to condense. It needs help. It needs what atmospheric physicists call a condensation nucleus, but what you and I can call a tiny piece of floating garbage. And oh, the sky is full of garbage. Beautiful, essential, cloud-making garbage. Every cubic centimetre of air above your head contains between 100 and 10,000 microscopic particles. Dust from deserts, salt crystals from ocean spray, pollen from flowers, sulfate compounds from volcanic eruptions, smoke from wildfires, even bacteria and fungal spores that have been lofted into the atmosphere by updrafts. Some of these particles are less than a micrometer across, smaller than the wavelength of visible light. Others are chunky by atmospheric standards, maybe 10 or 20 micrometers, and water vapour loves them. Loves them. Because these particles solve the fundamental problem of condensation. They give water molecules a place to gather without having to convince each other to go first. Picture it like this. You're a water molecule tumbling through the air, bouncing off nitrogen and oxygen molecules 1 billion times per second. The temperature drops slightly. Maybe you've risen a few hundred meters and the air pressure is lower, which means things are cooler. Suddenly you bump into a grain of sea salt, a microscopic cube of sodium chloride that got launched into the sky when a wave broke somewhere over the Pacific 3 days ago. Salt is hygroscopic, which is a fancy way of saying it's desperately thirsty. Its crystalline structure is covered in ions that yank at the electrical charge in your water molecule like tiny magnets. You stick. Then another water molecule bumps into you, and it sticks. Then another. Within seconds, there are thousands of you piling onto this single grain of salt, forming a spherical shell of liquid water. Around it, you've stopped being vapour. You've become a cloud droplet. This is happening right now, constantly, in every direction you could point. Billions of condensation nuclei playing host to trillions of water molecules, each microscopic transaction turning invisible into visible. And here's where it gets weirdly competitive. Not all nuclei are created equal. Sea salt is an excellent nucleus because it's hygroscopic and because it's relatively large, giving water molecules a nice surface area to work with. Sulfate particles from industrial pollution are even better. They're smaller but more chemically attractive to water, so they can grab vapour at lower humidity levels. Dust is okay, but not great. Pollen works in a pinch. Black carbon from diesel exhaust is surprisingly effective, which is why cities often have hazier skies than rural areas, even when the humidity is the same. There's an entire lottery happening in the sky, and the winners become clouds. The losers just keep drifting, waiting for their moment. Some of those particles will circle the globe for weeks before they finally snag enough water vapour to matter. Others will fall out of the atmosphere during the next rainstorm, getting scavenged by bigger droplets on their way down. It's chaos wrapped in probability, and the only reason it produces something as organised as a cloud is because there are so many particles playing the game that statistics smooth everything out into patterns. You know what's darkly funny? Humans have accidentally become one of the best cloud-making species on the planet. Every factory smokestack, every jet engine, every coal power plant pumps out condensation nuclei by the trillions. We've increased the particle count in certain parts of the atmosphere by factors of 10 or even 100 compared to pre-industrial levels. which means we've changed how clouds form, how dense they are, how reflective they are, how long they last. We're not just watching clouds, we've been editing them for the past century and a half, often without realizing it. But we'll get to that later. Right now, we're still in the moment of birth. So, you've got your condensation nucleus, your grain of salt or speck of sulfate. Water vapor has found it, condensed around it, and formed a droplet. Congratulations. You're now 10 micrometers of liquid water floating in the sky. You weigh essentially nothing, about 1/1000th of a gram. Gravity is pulling on you, sure, but air resistance is pushing back with almost equal force, so your terminal velocity is about 1 centimeter per second. At that speed, it would take you nearly a full day to fall from cloud height to the ground. You're not going anywhere fast, but you're also not staying still, because now the real party begins. You're about to get caught in the updraft engine, and that's going to change everything about your short, complicated life as a cloud droplet. So you're rising, the air is cooling, and more water vapor around you is deciding to give up and condense. New droplets are forming constantly, all around you, like stars blinking into existence. The cloud is growing from the inside out, and here's the beautiful part. As more vapor condenses, it releases more heat, which warms the air parcel slightly, which makes it even more buoyant, which makes it rise even faster, which cools it more, which condenses more vapor, which releases more heat. It's a feedback loop, a self-reinforcing engine. On days when the atmosphere is unstable, when there's lots of moisture and lots of heat at the surface, this engine can run wild. Updrafts in severe thunderstorms have been clocked at 50 meters per second, which is 180 kilometers per hour, which is faster than most hurricanes. You think you're just floating in a peaceful summer cloud. You're inside a machine that could, under the right conditions, become a monster. But today it's calm. Today it's just a fair weather cumulus, the kind that dots the sky on a pleasant afternoon. The updraft is maybe 2 or 3 meters per second. Brisk, but not violent. You ride it upward, along with billions of your fellow droplets, and the cloud builds. The bottom of the cloud, the part you can see from the ground, is called the cloud base, and it marks the altitude where the rising air has cooled enough for condensation to begin. Below the cloud base, the air is clear. Above it, it's full of droplets. The cloud base is usually flat and well-defined because the temperature-pressure relationship is consistent. Condensation starts happening at a specific altitude, give or take a few meters, across the entire updraft column. You rise past the cloud base. You're now officially inside the visible cloud, part of the white puff that someone on the ground is staring at and thinking isn't moving. You rise another 100 meters, another 200. The updraft is weakening now as it spreads out horizontally, trading vertical speed for lateral spread. You're approaching the top of the cloud where the updraft finally stalls. The air has risen as far as it's going to rise, at least for now. It's reached an altitude where it's the same temperature as the surrounding atmosphere, so there's no more buoyancy, no more lift. You slow, you stop rising, and for a moment you hover at the cloud summit, suspended in the sky, neither rising nor falling. But gravity hasn't forgotten about you. It never does. You're still a droplet of water, still slightly denser than air, still subject to Newton's laws. So you start to fall again, slowly, drifting downward at your 1 centimeter per second terminal velocity. Except now you're falling through a cloud full of other droplets, and every single one of them is a collision waiting to happen. That's when the real chaos begins, when you stop being a passive passenger in the updraft and start becoming an active participant in the collision choreography that turns cloud droplets into raindrops. But you're not ready for that yet. Right now, you're just hovering, suspended in a moment of perfect balance between the forces that want to lift you and the forces that want to pull you down. And from the ground, the person with the sore neck sees a cloud that hasn't moved an inch. You're a 10 micrometer droplet now, freshly condensed around your little nucleus of salt or sulfate, and you're falling at 1 centimeter per second, which is barely falling at all. It's more like drifting. You're a dust mote in a sunbeam. You're a snowflake in a snow globe. And then, without warning, you're not falling anymore. You're rising, fast. You've just been scooped up by an updraft, and suddenly you're travelling upward at speeds between 1 and 10 meters per second. That's up to 36 kilometers per hour. Highway speed, except you're going vertical and you're the size of a bacterium. Welcome to the engine room of the cloud. Here's what's happening beneath you, down at ground level where the sun has been baking the earth all morning. Solar radiation hits the surface. A parking lot, a ploughed field, a patch of dark soil, and converts into heat. That heat warms the air in contact with the ground. Warm air is less dense than cool air because the molecules are moving faster, bouncing around with more energy, spreading themselves out. Less dense means more buoyant. So that parcel of warm air starts to rise, the same way a hot air balloon rises, except there's no balloon, just an invisible blob of atmosphere that suddenly decided it would rather be higher up. And as it rises, it carries everything with it. Dust, pollen, moisture, and you, the tiny droplet that thought it was falling. This is convection, the same force that makes soup swirl in the pot and lava lamps blob upward. But in the atmosphere, convection is enormous. A single updraft column can be hundreds of meters wide and stretch from the ground to several kilometers up. Inside that column, the air is rising continuously, like an invisible elevator shaft with no elevator, just a constant upward flow. And you, droplet, are trapped in that flow. Your pathetic 1 centimeter per second downward drift is nothing compared to the updraft's multi-meter per second lift. You're being carried upward whether you like it or not. As you rise, the air around you expands. This is crucial. At ground level, the weight of all the atmosphere above presses down with significant force, about 1 kilogram per square centimeter or 14 pounds per square inch if you're American and stubborn. But the higher you go, the less atmosphere is above you, so the pressure drops. Lower pressure means the air expands, and when air expands it cools. This is called adiabatic cooling, and it's not because you're getting closer to the cold vacuum of space or farther from the warm ground. It's pure thermodynamics. The molecules in the air parcel are doing work to push against the lower external pressure, and that work costs energy, which comes out of their heat budget. Temperature drops about 10 degrees Celsius for every kilometre you rise, assuming the air is dry. If there's moisture condensing out, which there is because you exist, it drops slower, maybe 6 or 7 degrees per kilometre, because condensation releases latent heat, but it still drops. You're suspended near the top of the cloud now, and you've got company. Billions of other droplets are hovering around you, each one roughly the same size, each one caught in the same delicate balance between rising air and falling water. From a distance, you all look uniform, a smooth white surface like whipped cream or cotton. But up close, you're a swarm, a three-dimensional blizzard of tiny spheres moving in every direction at once, and you're about to start bumping into each other. Here's the thing about cloud droplets. They're terrible at staying apart. The air currents inside the cloud are turbulent, chaotic, full of little eddies and swirls that push droplets into different trajectories. Some droplets are slightly larger than others because they condensed around bigger nuclei or caught a better updraft. Larger droplets fall faster, not much faster, but enough. A 20 micrometer droplet falls about 8 times faster than a 10 micrometer droplet. So you've got this vertical sorting happening where bigger drops are sinking through clouds of smaller ones like lazy predators drifting through schools of fish. And when they collide, physics gets interesting. Sometimes they bounce. Seriously, you'd think 2 liquid droplets would merge on contact, but there's often a thin cushion of air between them that acts like a microscopic airbag. The droplets deform slightly on impact, flatten against that air cushion, then spring apart. It's like watching water balloons bounce off each other in extreme slow motion, except the balloons are microscopic and the slow motion is actually real time. But other times, maybe 1 collision in 10, maybe 1 in 5, depending on the droplet sizes and relative speeds, they stick. Their surfaces touch, the air cushion fails, and surface tension does its thing. The 2 droplets merge into 1 larger droplet, and now that combined droplet is heavier, so it falls faster, which means it's going to collide with even more droplets on its way down. It's a growth cascade. This process is called collision coalescence, and it's one of the main ways that rain forms in warm clouds where temperatures stay above freezing. A typical cloud droplet is 10 to 20 micrometers across. A typical raindrop is 1 to 5 millimeters across. That's 50 to 500 times bigger in diameter, which translates to somewhere between 125,000 and 125 million times bigger in volume. You're not going from droplet to raindrop through gradual accumulation of vapor. That would take forever. You're doing it through thousands of collisions, each one adding mass, each one making you fall faster, each one increasing your collision cross-section, so you sweep up even more droplets like a snowball rolling downhill. But here's the puzzle that confused scientists for decades. Collision coalescence is slow, really slow. To grow a droplet from cloud size to rain size through collisions alone takes at least 30 minutes to an hour, and that's under ideal conditions. But radar observations show that rain often starts falling from clouds within 15 or 20 minutes of the cloud forming. So what's going on? How do you speedrun droplet growth? The answer, it turns out, is that not all droplets start equal. Remember those condensation nuclei from earlier? These salt grains and sulfate particles and dust specks? Some of them are bigger than others. A giant sea salt nucleus, we're talking 50 or 100 micrometers across, which is massive by atmospheric standards, can grab so much water vapor that it forms what's called a giant condensation nucleus droplet. These lucky droplets start life already 20 or 30 or even 50 micrometers across. They're born big. And because they're big, they fall faster from the beginning, which means they start colliding and collecting smaller droplets immediately. They're the fast-track droplets, the overachievers, the ones that are going to become raindrops while everyone else is still figuring out which way is down. You, unfortunately, are not one of these giant droplets. You started on a normal-sized nucleus, so you're stuck in the slow lane. You're drifting downward at your leisurely 1 centimeter per second pace, occasionally bumping into other droplets. Most of the collisions result in bounces. Every so often you merge with someone, grow a tiny bit larger, fall a tiny bit faster. It's incremental. It's frustrating. You're like a player in a video game trying to level up by fighting the lowest tier enemies while someone else spawned with a legendary weapon and is already at the final boss. But you're not alone in your mediocrity. Most of the droplets in the cloud are in the same situation. The cloud is full of 10 to 20 micrometer droplets, all slowly trying to grow through collisions. Some will make it, most won't. Because here's the other complication. You're still inside the updraft zone, at least partially. The air currents keep shifting. Sometimes you drift downward into a region where the updraft is stronger, and suddenly you're being carried back up again. You're caught in a loop, rising and falling within the cloud's internal circulation, colliding and merging and occasionally getting separated again if the turbulence is strong enough to rip larger droplets apart. It's not a straight path from cloud droplet to raindrop. It's a chaotic, random walk with occasional progress. And the whole time this is happening, the bouncing, the merging, the rising, the falling, the cloud from the outside looks completely still. The person on the ground sees a white puff that might have drifted slightly to the east, on the prevailing wind, but otherwise appears frozen in place. They have no idea that you and your billion companions are running a collision derby in there, that every second brings thousands of impacts, that some droplets are winning the size lottery, while others are stuck in suspended animation. The cloud is a battlefield disguised as a pillow. You've merged with maybe 5 or 6 other droplets by now. You're up to 40 micrometers in diameter. Your terminal velocity has quadrupled. You're starting to feel like you're getting somewhere. And then you drift into a particularly violent pocket of turbulence, and everything you thought you knew about falling gets thrown into a 3-dimensional blender set to chaos mode. You've been tumbling through turbulence for what feels like an eternity, but has actually been about 90 seconds. You've collided with maybe 20 other droplets, some successful mergers, some just glancing bounces. You're now 60 micrometers across. You're falling faster, maybe 5 centimeters per second now instead of 1. You're starting to become a meaningful player in the cloud's ecosystem. And then you drift into a particularly cold region of the cloud, a zone where the temperature has dropped below freezing, and suddenly you're not just dealing with liquid water dynamics anymore. You're about to meet ice, and ice plays by completely different rules. But before we get there, take a moment to appreciate what turbulence has done for you. It's the reason clouds are thick and textured instead of thin and wispy. It's the reason droplets grow fast enough to make rain. It's the reason that when you look at the edge of a cloud, you see those cauliflower-like bumps and billows instead of a smooth surface. Every bump is a turbulent eddy that got big enough to deform the cloud boundary. Every wisp tearing off the edge is turbulence entropy, mixing cloud with non-cloud until the distinction blurs. The cloud looks still from the outside, but inside it's a turbulent nightmare, and that nightmare is exactly what makes the cloud work. Chaos builds order, disorder creates structure, and you, droplet, are living proof that sometimes the best way to grow is to get thrown into a blender and see what sticks. Turbulence is one of those words that sounds worse than it is when you're on an airplane. The seatbelt light comes on, your drink jiggles a little, someone's stomach does a flip. But inside a cloud, turbulence is the dominant force. the organising principle, the thing that turns a boring collection of water droplets into a churning, mixing, droplet-smashing factory. And you've just drifted into a region where the turbulence is having a particularly aggressive day. Here's what turbulence actually is. It's the breakdown of smooth, orderly airflow into chaotic, swirling motion at multiple scales. Imagine stirring cream into coffee. At first, you get these big lazy spirals following your spoon, but keep stirring, and those big spirals develop smaller spirals at their edges, and those smaller spirals develop even tinier spirals, and eventually you've got motion happening at every size scale, from the width of the cup down to fractions of a millimeter. That's turbulence. It's a cascade of energy from large eddies to small eddies to microscopic eddies, and it doesn't stop until molecular viscosity, the stickiness of the fluid itself, finally smears out the smallest motions into heat. In the atmosphere, turbulence starts big. You've got the updraft column itself, which is an organised flow on the scale of hundreds of meters. But that updraft isn't perfectly smooth. Its edges are unstable, peeling off chunks of rising air that twist into vortices. Those vortices spawn smaller vortices. The smaller ones spawn tinier ones. By the time you're down at the scale of centimeters, your scale, droplet scale, the air is a three-dimensional maze of currents moving in every conceivable direction. Some parcels of air are spinning clockwise, others counterclockwise. Some are stretching horizontally, others compressing vertically. There's no up or down anymore, at least not in any consistent sense. There's just motion, constant and chaotic. And you, a 40 micrometer droplet trying to fall sedately through this mess, are getting absolutely thrashed. One moment you're moving downward at a decent clip. The next moment you've been caught in an eddy that's spinning you sideways and upward. Then you're flung into a downdraft, a small pocket of sinking air, and you're suddenly falling at 10 times your normal speed. Then you hit a wall of air that's moving the opposite direction and you almost come to a complete stop. Your trajectory looks like it was drawn by a drunk spider. And this is happening to every single droplet around you. You're all being stirred together like ingredients in a blender, except the blender is invisible and the size of a building. This is actually great news for cloud development, even if it feels like abuse from your perspective. Turbulence does two critical things. First, it brings droplets into contact with each other far more efficiently than simple settling would. Remember how you were slowly drifting downward, hoping to bump into smaller droplets? Turbulence throws you into packs of them. It creates regions of high droplet concentration where collisions happen at 10 or 20 times the normal rate. Some eddies actually centrifuge droplets outward, concentrating them at the edges of vortices the way dust collects in the corners of a room. Where there's concentration, there's collision. Where there's collision, there's growth. Second, turbulence mixes different parts of the cloud together. Near the cloud edges, where dry air from outside is being entrained, sucked into the cloud by pressure differences, there are droplets that are starting to evaporate. They're shrinking, dying, turning back into vapor. But turbulence grabs those evaporating droplets and mixes them with fresh droplets from the updraft core, where conditions are humid and stable. It stirs together air parcels with different temperatures, different moisture contents, different histories. This mixing is what gives clouds their complex internal structure. Without turbulence, you just have a boring vertical gradient, warm and moist at the bottom, cool and dry at the top. With turbulence, you've got a patchwork, a mosaic of microclimates, each one affecting the droplets inside it differently. There's a specific type of turbulence that scientists are still trying to fully understand, and it's called small-scale clustering. Basically, turbulence doesn't just stir droplets randomly, it actually creates patterns. Droplets of similar sizes tend to cluster together in certain types of turbulent flows, like marathon runners of similar speeds naturally forming pace groups. These clusters can be incredibly dense, with droplet concentrations 10 or even 100 times higher than the surrounding cloud. And in these clusters, the collision rate goes through the roof. It's like rush hour traffic versus open highway. When everyone's packed together, fender benders happen constantly. Except instead of fender benders, you're getting droplet mergers. You've drifted into a colder neighbourhood now, a region of the cloud where the updraft has carried you high enough that the temperature has dropped below 0 degrees Celsius. And yet, miraculously, you're still liquid. You're supercooled. Water that's below its freezing point but hasn't actually frozen yet. This should feel impossible, but it's completely normal in clouds. In fact, most clouds between about -5 and -15 degrees Celsius are full of supercooled water droplets just like you, hanging out in a thermodynamically unstable state, waiting for something to trigger the phase change. You're a loaded gun that hasn't been fired yet. The reason you haven't frozen is the same reason water vapor had trouble condensing earlier. You need a nucleation site. Freezing doesn't just happen spontaneously in pure water, even when it's cold. The water molecules need to arrange themselves into a crystalline lattice, and that arrangement requires a template, a seed, something to get the process started. In a lab, in perfectly pure water, you can supercool down to -40°C before homogeneous nucleation kicks in. That's when the water molecules finally organize themselves into ice crystals through sheer random chance. But in the real atmosphere, at the temperatures you're experiencing, you need help. You need an ice nucleus. Ice nuclei are rarer than condensation nuclei, much rarer. For every one particle in the atmosphere that can trigger ice formation at -10°C, there are 10,000 particles that can trigger water condensation. Ice nuclei need to have a crystalline structure that matches ice's hexagonal lattice, at least approximately. The best ice nuclei are mineral dust particles, clay especially, because their crystal structure happens to align nicely with ice. Certain types of bacteria also work beautifully. They've evolved proteins that template ice formation, probably as a survival strategy. Some pollen grains are decent. Sea salt, despite being a champion condensation nucleus, is terrible at nucleating ice. And right now, you don't have an ice nucleus. Your core is still that grain of sea salt from way back when you first condensed. So you're just floating here, supercooled and liquid, in a cloud that's a few degrees below freezing. You're metastable, which is a physicist's way of saying you're technically fine, but one wrong move and everything changes. Then, 3 meters away from you, a dust particle from Mongolia, it's been circling the globe in the upper atmosphere for 2 weeks, finally finds itself inside a supercooled droplet that does have the right crystalline structure. The ice lattice clicks into place. The droplet freezes, transforming from liquid sphere to tiny ice crystal in a matter of seconds. And that's when the molecular heist begins. Here's the physics. Ice and liquid water can coexist at the same temperature, but they have different vapor pressures. Vapor pressure is basically a measure of how eagerly molecules want to escape from a surface. Liquid water at -10°C has a higher vapor pressure than ice at the same temperature, which means water molecules evaporate more readily from liquid surfaces than they do from ice surfaces. But it also means water molecules are more eager to deposit onto ice surfaces than back onto liquid surfaces. The equilibrium is skewed, ice is energetically favoured. So now you've got a situation where the air around the newborn ice crystal is exactly saturated with respect to liquid water, meaning liquid droplets like you're in perfect equilibrium, neither growing nor shrinking. But that same air is supersaturated with respect to ice, meaning the ice crystal is in a growth environment, a candy store, a buffet. Water molecules start depositing onto the ice crystal's surface. It grows. As it grows, it pulls water vapor out of the air. As vapor gets pulled out, the surrounding air becomes slightly less saturated, and suddenly you, the nearby supercooled droplet, find yourself in air that's undersaturated with respect to liquid water. Your surface starts evaporating. You're losing molecules. They're leaving your surface, entering the vapor phase, drifting over to the ice crystal, and depositing there. You're being cannibalized. Your mass is being stolen by a thief made of frozen water, and there's nothing you can do about it because thermodynamics doesn't care about your feelings. This is the Bergeron process, named after the Swedish meteorologist who figured it out in the 1930s, and it's one of the most elegant and ruthless mechanisms in cloud physics. The ice crystal grows rapidly. Within minutes, it's hundreds of micrometers across, then millimeters. It develops the classic six-fold symmetry of ice, growing into a hexagonal plate or a stellar dendrite. Those gorgeous snowflake shapes you see in children's books. The exact shape depends on temperature and humidity, but the growth is fast and obvious. Meanwhile, you and the other supercooled droplets in the vicinity are shrinking. You're evaporating to feed the ice crystal's growth. You've gone from 60 micrometers down to 50, then 40. You're losing the size you worked so hard to gain through all those collisions, and you can't stop it. This is happening all over the cold upper regions of the cloud, wherever ice crystals form, and they're forming constantly now, triggered by every dust particle and bacterium and ice-nucleating aerosol that drifts into a supercooled droplet. The Bergeron process kicks in. Ice grows at the expense of liquid water. The cloud's character is changing from a suspension of water droplets to a mix of droplets and ice crystals. and eventually to mostly ice crystals as the liquid water supply gets depleted. The transformation is invisible from the outside. The cloud still looks white and fluffy, but internally it's undergoing a phase transition, a restructuring of its fundamental composition. And here's the kicker. Ice crystals fall faster than water droplets of the same mass because they have weird shapes, plates, needles, dendrites, that give them more air resistance per unit of weight, but they're also much larger than droplets, so overall they descend faster. A snowflake can fall at 1 or 2 meters per second, which is 100 times faster than you are falling as a droplet, so the ice crystals start raining out of the upper cloud, descending toward warmer air. If they make it through the 0-degree level and into above freezing temperatures, they melt and become raindrops. If the air below is cold enough, they stay frozen and reach the ground as snow. You, meanwhile, have evaporated down to nothing. You're vapor again, invisible, dispersed. Your brief career as a cloud droplet is over. Your substance donated unwillingly to an ice crystal that's now falling away beneath you. It's a little tragic, honestly, but it's also the mechanism that makes precipitation efficient in mixed-phase clouds that contain both liquid water and ice. Without the Bergeron process, rain formation would be much slower and much less reliable. The molecular heist is brutal, but it works. And somewhere far below, someone might open their palm and catch the snowflake that used to be you, never knowing the theft that made it possible. Let's talk about what happens when you rub a balloon on your hair and it sticks to the wall. Except instead of a balloon, it's a chunk of ice the size of a grape, travelling at 60 kilometers per hour through a cloud. And instead of your hair, it's millions of other ice particles. And instead of sticking to a wall, the end result is a lightning bolt that could vaporize you. Because clouds don't just make rain, they make electricity, enormous quantities of it. And that placid summer cumulus you're staring at might be quietly building up enough voltage to power a small city for a microsecond. Ice is the key. Liquid water clouds rarely generate much electrical activity. But once you get ice crystals into the mix, once the Bergeron process starts cranking out snowflakes and grapple and frozen droplets, you've essentially built a giant static electricity generator in the sky. And it all comes down to collisions, which you should be familiar with by now, except these collisions don't just merge particles, they transfer charge. Here's the basic setup. In the cold upper regions of a cloud, you've got 2 main types of ice particles bouncing off each other. First, you've got small ice crystals. The snowflakes, the needles, the hexagonal plates. These are relatively light and tend to stay suspended in the updraft or fall slowly. Second, you've got grapple, which is what happens when supercooled water droplets collide with an ice crystal and freeze on contact. Grapple particles are lumpy, irregular pellets of rime ice, and they're heavier than regular ice crystals, so they fall faster. Picture tiny hailstones, soft and opaque, tumbling through the cloud. They're like the bullies of the ice particle world, bigger, denser, falling with purpose. When a grapple particle collides with a smaller ice crystal, something strange happens at the microscopic level. The collision isn't perfectly elastic. The surfaces scrape against each other, deform slightly, rebound, and during that split-second interaction, charge transfers from one particle to the other. Scientists are still debating the exact mechanism. It probably involves differences in surface temperature, or the presence of microscopic liquid layers on the ice surfaces, or the way ions distribute themselves in the crystal lattice, but the result is consistent. The grapple particle picks up a negative charge, and the smaller ice crystal picks up a positive charge. Now the small ice crystal, positively charged, gets carried upward by the updraft. It's light, it's buoyant, it rises. The grapple particle, negatively charged, falls. It's heavy, gravity wins, it descends. Do this billions of times, billions of collisions, billions of charge transfers, and you start to develop a charge separation in the cloud. Positive charge accumulates in the upper regions. Negative charge accumulates in the middle and lower regions. You've built a battery. A giant, fluffy, extremely dangerous battery floating in the sky. The voltage difference grows. In a typical thunderstorm cloud, the charge separation can reach 100 million volts or more between the upper positive region and the lower negative region. That's enough voltage to make your hair stand on end from a kilometre away if you could somehow feel it directly. The electric field strength inside the cloud reaches about 100 kilovolts per metre, near the regions of maximum charge. For comparison, a tiny spark jumping between your finger and a doorknob involves maybe 1,000 volts over a few millimetres. This is that times 100,000. sustained across kilometers of cloud. But air is an excellent insulator. Under normal conditions, it takes an electric field of about 3 million volts per meter to break down air and create a spark. The cloud's electric field is strong, but not quite that strong, so for a while nothing happens. The charge just keeps building. More collisions, more separation. The invisible battery charges higher and higher. The cloud from the outside still looks peaceful, maybe a little darker at the base where all the precipitation is forming, but otherwise just a cloud doing cloud things. Inside, it's a powder keg. Then something tips the balance. Maybe a particularly conductive column of ionized air forms spontaneously. Maybe a cosmic ray streaks through the cloud, ionizing a path. Maybe the electric field in one small region fluctuates just high enough to start a cascade. Whatever the trigger, air begins to break down. Free electrons accelerate in the electric field, slam into air molecules, knock more electrons loose. Those electrons accelerate and slam into more molecules. It's a chain reaction, an avalanche of ionization, creating a branching path of conductive plasma through the cloud. This is the stepped leader, a finger of electricity probing downward from the negative charge region, searching for the ground or for a pocket of positive charge to neutralize against. The stepped leader branches and zigzags because it's following the path of least resistance, which in turbulent air is chaotic. It moves fast, but not instantaneously, maybe 100 kilometers per second, which sounds fast but is still a third the speed of light. When it connects with the ground, or with the positive charge region in the upper cloud, or with a leader coming from another cloud, the circuit completes. And then the main discharge happens, the return stroke. All that stored charge drains through the conductive channel in a fraction of a millisecond. The current can reach 200,000 amperes. The channel heats to 30,000 Kelvin, which is 5 times hotter than the surface of the sun. The air explodes outward in a shock wave. You hear it as thunder. Lightning inside clouds, intra-cloud lightning, is actually more common than cloud-to-ground strikes. These are the flashes you see that illuminate the entire cloud from within, like a lamp turning on behind a curtain. They're travelling between the charge regions inside the cloud structure, balancing out the voltage differences that built up through all those ice crystal collisions. And then the collisions start again, and the charge separation starts building again, and a few minutes later, another flash. The cloud is breathing electricity, inhaling charge through collisions, exhaling it through lightning. You know what's wild? Every second, somewhere on Earth, there are about 100 lightning strikes happening. That's 8 million strikes per day. The atmosphere is constantly churning out electrical storms, constantly building and discharging these enormous voltages, all because ice particles can't bump into each other without swapping electrons. It's one of the planet's fundamental rhythms, like a heartbeat, except it's made of frozen water and plasma, and it's happening inside clouds that, from the right angle, look like they're barely moving. The still cloud is a capacitor. The still cloud is a bomb. The still cloud is waiting for the moment to remind you that it contains more power in a single discharge than your house uses in a month. And all of that power was built one collision at a time by ice particles you can't even see. Let's rewind. You're not an ice crystal or a Graupel pellet or a lightning bolt. You're back to being a droplet. Let's say you reformed from vapor after your Bergeron sacrifice, found a new condensation nucleus, started the whole process over. You've grown to maybe 30 micrometers through a few lucky collisions, and now you're drifting toward the edge of the cloud. This is not a good place to be. The edge of a cloud is where droplets go to die. Here's what's happening at the boundary. Inside the cloud, the air is saturated, 100% relative humidity, maybe even slightly supersaturated in the active updraft regions. Water vapor and liquid water are in equilibrium. Droplets aren't shrinking or growing from vapor exchange. They're stable, content, maintained. But 3 meters outside the cloud, the air is clear and dry. Relative humidity might be 60 or 70%. That air is undersaturated, hungry for moisture, and it's mixing with the cloud edge through the same turbulence that's been throwing you around this entire time. Dry air gets entrained into the cloud, pulled in by pressure gradients, by the turbulent eddies peeling off the cloud boundary, by the general chaos of atmospheric mixing. Tendrils of dry air penetrate into the cloud like fingers, and wherever they touch, droplets start to evaporate. It's not dramatic, there's no boiling or hissing. The water molecules on your surface simply have enough thermal energy to overcome the intermolecular forces holding them in the liquid phase, so they leap off into the vapor phase and disperse into the surrounding air. One molecule at a time, you're shrinking. Evaporation is an endothermic process. It requires energy, specifically the latent heat of vaporization, which is about 2.5 million joules per kilogram of water. That energy comes from the droplet itself. As molecules evaporate, they carry away heat, cooling the droplet that remains. So you're not just shrinking, you're getting colder. And the air around you, which is gaining water vapor and the heat that came with it, is getting slightly warmer and more humid. You're in a race now. Can you drift back toward the cloud core where the air is saturated and you'll stop evaporating before you shrink down to nothing? Probably not. The edge of the cloud is a killing field. Most droplets that drift into the entrainment zone evaporate completely within minutes. They contribute their mass back to the vapor phase, humidifying the dry air, and in doing so they actually slow down the entrainment process slightly. The dry air becomes less dry as it eats droplets, so it becomes less aggressive. But that's cold comfort when you're the one being cannibalized. You're 30 micrometers across, then 25, then 20. The evaporation rate accelerates as you get smaller because your surface area to volume ratio increases. A small droplet has proportionally more surface for its mass, which means more evaporation per unit of remaining water. This is why clouds have such sharp, well-defined edges when you look at them from the right angle, but wispy, dissolving boundaries when you look from another angle. The sharp edges are where the entrainment is weak or where the updraft is strong enough to keep replenishing the boundary with fresh droplets. The wispy edges are where entrainment is winning, where dry air is mixing in faster than the cloud can resupply moisture. You're watching evaporation in real time. Those little wisps that tear off a cumulus cloud and then vanish within seconds, those are entire populations of droplets evaporating back into invisibility. They had their moment as part of the visible cloud, and now they're gone, reclaimed by the vapor phase. From the ground, this looks like the cloud is slowly shrinking or changing shape. The edges seem to recede, or a piece breaks off and dissolves. But you're not watching the cloud move, you're watching it eat itself. Every cloud is constantly losing mass to evaporation at its boundaries. The only reason the cloud persists at all is because the updraft core is constantly supplying new moisture, condensing new droplets, replenishing what's lost. It's a dynamic equilibrium, a tug of war between condensation and evaporation, and the cloud is just the region where condensation is currently winning. In stable conditions, this equilibrium can last for hours. The cloud looks stationary because the updraft and the entrainment are roughly balanced, so the cloud maintains approximately the same size and shape, even though the specific droplets making up the cloud are constantly cycling. New ones forming in the center, old ones evaporating at the edges. It's like a waterfall, the water is always moving, always changing, but the shape of the waterfall stays the same. You're not looking at a thing, you're looking at a process that's temporarily organized into something that looks like a thing. But when conditions become less stable, when the updraft weakens, or when the surrounding air gets drier, or when the sun sets and the ground stops heating, the balance tips. Evaporation starts winning. The cloud begins its death spiral. The edges dissolve faster than the core can replenish them. The cloud base rises as the lower regions evaporate away. The cloud becomes thinner, wispier, less opaque, and eventually, sometimes within 10 or 15 minutes, the entire cloud just vanishes. Every droplet evaporated, every bit of liquid water returned to the vapor phase. The cloud didn't go anywhere. It didn't blow away or rain out. It simply ceased to exist as a visible object. You're 15 micrometers now, then 10, then 5. Your sea salt nucleus is still there at your core, the same grain that started this whole adventure, but the water shell around it is almost gone. The air around you is getting more humid as you and millions of your fellow droplets sacrifice yourselves, but it's not enough. The dry air keeps coming, and then you hit the critical size, maybe 2 or 3 micrometers, where you're barely more than a haze nucleus, a microscopic particle with a thin film of water. One more gust of dry air, one more minute of evaporation, and the water film vanishes completely. You're just a salt grain again, floating in clear air, waiting for the next cloud to form around you. The person on the ground watches the cloud thin out and disappear. They might think it drifted away, or that the wind blew it apart, or that it somehow transformed into the clear air around it. They're not entirely wrong about that last one. The cloud did become the clear air. It donated its water molecules back to the vapor phase, humidifying the atmosphere, cooling the local environment, slightly through evaporative cooling. The cloud didn't go nowhere, it went everywhere. It diffused, dispersed, became part of the invisible reservoir of moisture that the next cloud will draw from. You're back where you started, except the air is slightly different now, and when the next updraft comes through and the next condensation event begins, you'll do it all over again. The cloud is dead. Long live the cloud. While evaporation is dissolving the edges of the cloud and turning droplets back into vapour, there's another force at work reshaping the cloud from the outside. Wind shear. And wind shear is why that puffy cumulus that looked like a cotton ball 20 minutes ago now looks like it's been stretched sideways, smeared across the sky like someone dragged their thumb through wet paint. The cloud isn't moving as a solid object. It's being pulled apart by invisible hands moving at different speeds. Here's the setup. The atmosphere is layered, and each layer has its own wind speed and direction. Near the ground, friction with the surface slows everything down. Trees, buildings, hills, they all create drag that saps energy from the moving air. So surface winds might be blowing from the west at 10 km per hour, but go up a kilometre above the friction layer, and the wind might be blowing from the west at 30 km per hour. Go up 2 kilometres, and it's 45 km per hour, but now from the west-northwest. The wind speed increases with altitude, and the direction can rotate slightly. This variation of wind with height is wind shear, and clouds hate it. Imagine you're a cloud, a whole cloud this time, not just a droplet. Your base is at 1 kilometre altitude, sitting in the 15 km per hour wind layer. Your top is at 3 kilometres, sitting in the 50 km per hour layer. The wind at your top is blowing 3 times faster than the wind at your bottom. What happens? You get stretched. The upper part of the cloud gets blown downwind faster than the lower part. The cloud develops a lean, a tilt, an angled structure. In moderate wind shear, cumulus clouds often develop that classic slanted look, where the updraft pushes material vertically, but the wind shear immediately smears it sideways, creating a tower that leans like it's drunk. In strong wind shear, the kind you get in severe thunderstorm environments, things get more dramatic. The updraft might be punching upward at 10 or 20 meters per second, trying to build a towering cumulonimbus. But the wind at the top is screaming along at 80 or 100 kilometers per hour, 50 kilometers per hour faster than the wind at the base. The top of the cloud gets ripped off and blown downwind, spreading out into that characteristic anvil shape you see on storm clouds. The anvil is just the top of the cloud that hit the tropopause, the boundary between the troposphere and stratosphere, where the atmosphere suddenly gets warmer with altitude and updrafts can't penetrate, and then got sheared sideways by high-altitude winds. It spreads out horizontally because it can't go up anymore, and the wind shear stretches it into a flat, anvil-shaped shelf that can extend for dozens of kilometers downwind from the main updraft. From the ground, this looks like the storm is moving, and it is, but not as a coherent unit. The anvil is getting blown one direction. The main updraft core might be propagating in a different direction based on where new updrafts are forming. The precipitation region is falling and getting blown yet another direction. You're not watching one object move through space. You're watching different parts of a cloud system responding to different wind fields at different altitudes, all happening simultaneously, all creating the illusion of organised motion when really it's organised chaos. Wind shear does something else too. It can make clouds look like they're boiling or bubbling even when they're not particularly convective. The shear creates horizontal vortices, tubes of spinning air oriented parallel to the cloud boundary. These vortices roll along the cloud edge like invisible logs, and they create those undulating, wave-like patterns you sometimes see on the underside of clouds. The technical term is Kelvin-Helmholtz instability, and it's the same physics that creates ocean waves when wind blows over water. The boundary between two fluids moving at different speeds becomes unstable and develops waves. In clouds, those waves show up as billows or ripples, evenly spaced bumps along the cloud base or cloud edge. They're beautiful, hypnotic, and they're a direct visualization of wind shear doing its thing. But here's what's really happening to individual droplets when wind shear stretches the cloud. Remember, you're a droplet inside this structure, and you're being carried along by the air parcel you're embedded in. If your air parcel is near the top of the cloud, you're racing downwind at 50 kilometers per hour. If your neighbour droplet is in an air parcel 100 meters below you, it's only moving at 30 kilometers per hour. The cloud is being pulled apart vertically, stretched like taffy, and the droplets inside are being separated from each other along that vertical gradient. This has consequences for precipitation formation. Collision coalescence works best when droplets are packed close together and have lots of opportunities to bump into each other, but wind shear spreads them out, reduces the droplet concentration, makes collisions less frequent. In highly sheared environments, clouds can have trouble making rain because the droplets don't stay close enough together long enough to grow efficiently. The cloud gets tall and impressive looking but stays relatively precipitation free because its guts have been smeared across 10 kilometers of horizontal space. On the other hand, wind shear is essential for severe storm longevity. In a low shear environment, a thunderstorm updraft will build, rain will form, the rain will fall back down through the updraft, and the resulting downdraft, the cold air sinking back toward the ground, dragged down by the weight of precipitation, will choke off the updraft. The storm kills itself within 30 minutes, but in a high shear environment, the updraft gets tilted, so the precipitation falls downwind of where the updraft is rising. The downdraft and updraft are spatially separated. The storm can breathe. The updraft keeps feeding on warm, moist air from near the surface, and the precipitation falls harmlessly off to the side. These are the storms that last for hours, the supercells, the tornado producers. Wind shear is both a disruptor and an organizer, depending on context. So when you look at that cloud and it seems to be stretching horizontally, developing those long streamers trailing downwind, what you're seeing is the atmosphere's layered wind structure made visible. Every altitude has its own speed, its own direction, and the cloud is a three-dimensional object passing through all of them simultaneously. It's being sculpted by forces that are invisible everywhere except where the cloud happens to be. The cloud is an artist's brush dragged through still wet paint, except the hand holding the brush is moving at different speeds at different heights, and the paint is water droplets that are themselves falling and evaporating and colliding. The result is something that looks almost intentional, almost designed, but it's just physics doing what physics does when you give it moisture and heat and wind and let it play. You've probably never thought about why clouds are white. It's one of those facts that seem so obvious it doesn't need explaining. Clouds are white, snow is white, milk is white, and that's just how things are. But colour is light, and light is physics, and the whiteness of clouds is actually telling you something specific about the size of water droplets and the wavelengths of visible radiation. So let's talk about why that cloud you're staring at looks the way it does, and why it won't look that way in 20 minutes when the sun drops lower in the sky. Light from the sun is white, which is really a combination of all visible wavelengths: red, orange, yellow, green, blue, indigo, violet mixed together. When that white light hits a water droplet in a cloud, the droplet scatters it. Not absorbs it, not reflects it like a mirror, scatters it. The photons bounce around inside the droplet, refracting at the entrance surface, maybe reflecting off the back, refracting again at the exit, emerging in essentially random directions. And here's the key: water droplets in clouds are almost always between 5 and 50 micrometers in diameter, which is larger than the wavelengths of visible light. Visible light ranges from about 0.4 micrometers for violet to 0.7 micrometers for red. The droplets are 10 to 100 times bigger than the wavelengths they're scattering. When a scattering particle is much larger than the wavelength of light, it scatters all wavelengths equally. This is called me-scattering, and it's wavelength independent. Red photons get scattered the same amount as blue photons as green photons. So when white light enters the cloud and interacts with millions of droplets, it gets scattered in every direction, but it stays white because all the wavelengths are scattered equally. The cloud looks white because it's returning all the colours of sunlight back to your eyes in equal proportions. It's not favouring any wavelength. It's a perfectly democratic scatterer. Contrast this with the sky, which is blue. The sky is blue because of Rayleigh scattering, which happens when light interacts with particles much smaller than its wavelength, individual air molecules, which are less than 1 nanometer across. Rayleigh scattering is wavelength dependent. It scatters shorter wavelengths, blue and violet, much more efficiently than longer wavelengths, red and orange. So the blue light gets scattered all over the sky, and that's what you see when you look up. But clouds don't do Rayleigh scattering because water droplets aren't small enough. They're in the me-scattering regime, and me-scattering is white, except clouds aren't always white. Sometimes they're grey, sometimes they're almost black, sometimes they're brilliant gold or orange or pink or even purple. And that's where things get interesting because the colour of a cloud depends on thickness, on viewing angle, on the position of the sun, and on what's between you and the cloud. Let's start with grey. A cloud looks grey when it's thick enough that light can't penetrate all the way through. Sunlight enters the top of the cloud and starts getting scattered by droplets. Each scattering event sends photons in random directions, including sideways and backwards. The deeper the light penetrates into the cloud, the more scattering events it undergoes, and the more diffuse and weakened it becomes. In a thin cloud, maybe 100 meters thick, plenty of light makes it through to the bottom so the cloud base looks bright. But in a thick cloud, a kilometer or more, the light gets scattered so many times that very little reaches the bottom. The base of the cloud is in shadow, lit only by light scattered from the sides or reflected from the ground. It looks dark grey or even black. This is why the same cloud can look white on top and grey on the bottom. You're seeing the top illuminated by direct sunlight, and the bottom starved of light by its own thickness. And this is why storm clouds look so menacing. They're tall, they're thick with water and ice, and their bases are so far from the sun's direct illumination that they appear nearly black. It's not that they're made of different stuff, they're just optically thick. Now let's add some sun position. When the sun is high overhead, clouds look white or grey depending on their thickness. But when the sun is near the horizon, during sunrise or sunset, the light has to travel through much more atmosphere to reach the clouds. And during that long journey through the atmosphere, the blue wavelengths get rayly scattered away by air molecules. By the time the sunlight reaches the clouds, it's been filtered into oranges and reds and golds. The clouds scatter this already coloured light, so they take on those warm hues. That's your classic sunset cloud, illuminated from below or from the side by light that's already orange, scattering it faithfully, looking like it's on fire. The most dramatic colours happen when the sun is below the horizon from your perspective, but still illuminating high-altitude clouds from below. You're standing in shadow. The ground is in shadow. But there's a cirrus cloud 10 kilometres up that's still catching direct sunlight. That cloud scatters the deeply filtered sunset light, almost pure red by that point, and glows like an ember. Meanwhile, lower clouds are in shadow and appear dark blue or purple, because they're only lit by the scattered blue light from the rest of the sky. You get this layered effect. Purple clouds low down, gold and crimson clouds high up, all from the same sunlight filtered and scattered different amounts depending on geometry. There's also the issue of what's between you and the cloud. If you're looking at a distant cloud through several kilometres of hazy air, the light scattered by that cloud has to pass through all that intervening atmosphere before reaching your eyes. The haze, which is just a suspension of fine particles, scatters more light out of your line of sight, and it preferentially scatters shorter wavelengths. So distant clouds often look slightly blue or grey-blue, tinted by the atmosphere you're viewing them through. Close clouds look crisp and white. Distant clouds look washed out and blue-shifted. It's the same reason distant mountains look blue, and then there's optical depth and multiple scattering. In a really thick cloud, photons might scatter dozens or even hundreds of times before either exiting the cloud or being absorbed. Each scattering event randomizes the photon's direction. After enough scatterings, the light becomes completely diffuse. It's coming from everywhere and nowhere, with no memory of where the sun is. This is why being inside a cloud, inside fog, which is just a cloud at ground level, makes everything look uniformly grey and directionless. The light has been scattered so many times it's lost all its structure. You can't tell where the sun is. Everything is the same flat grey because every direction is scattering light toward you equally. So that white cloud, that innocent-looking puff that seems so simple, is actually a complex optical system. It's a three-dimensional scattering medium with variable thickness, variable droplet concentration, variable illumination angle, all interacting to produce the specific shade and brightness you see from your particular vantage point. Change any one variable, make the cloud thicker, move the sun lower, add some haze, and the colour changes. The cloud isn't white or grey or gold, it's all of them, depending on when and how you look. And the stillness, the apparent unchanging nature of that cloud, hides the fact that its colour is shifting subtly every second as the sun arcs across the sky, as the cloud's thickness fluctuates, as droplets evaporate at the edges and condense in the core. The colour is as dynamic as everything else. You're just not watching closely enough to notice. Let's ask a question that seems simple but isn't. How long does a cloud live? You look up at that cumulus, the one you've been tracking for the past 5 minutes, and it seems eternal. It was there when you started watching, it's there now, and you assume it'll be there when you go inside for dinner. But clouds are mortal. They have birth moments and death moments, and the time between those moments is usually measured in minutes to hours, not days. You're watching something die in slow motion, and you don't even realise it. A typical fair weather cumulus, the kind that dots the sky on a pleasant summer afternoon, lives for about 10 to 20 minutes. That's it. From the moment the updraft begins lifting moisture past the condensation level to the moment the last droplet evaporates back into invisibility, you've got maybe a quarter of an hour if the cloud is lucky. Some cumulus clouds make it to 30 minutes if conditions are particularly favourable. A few rare specimens might persist for an hour if they're in an environment with sustained updrafts and minimal wind shear, but most don't. Most are flashes in the pan, temporary sculptures carved by thermodynamics and then erased just as quickly. Here's the life cycle. The cloud begins when a parcel of warm, moist air at the surface becomes buoyant enough to overcome the inertia of the surrounding atmosphere and starts rising. Maybe it was triggered by heating over a parking lot, or by wind flowing over a hill, or by the collision of two different air masses. The exact trigger doesn't matter. What matters is that the air rises, cools adiabatically, and reaches the condensation level. Droplets form. The cloud base appears, a flat horizontal surface marking the altitude where vapor became visible. This is the birth moment, the point where the cloud transitions from abstract potential to concrete reality. For the next 5 to 10 minutes, the cloud grows. The updraft is strong, feeding the cloud with moisture and energy. Droplets form continuously in the rising air. The cloud builds vertically, developing that characteristic cauliflower texture as turbulent eddies create bumps and billows on its surface. From the ground, it looks like the cloud is inflating, puffing up, gaining volume and brightness. This is the cloud's adolescence, its growth phase, the period when everything is working in its favour. But even during this growth phase, the cloud is already dying at the edges. Entrainment is eating away at the boundaries, evaporating droplets, mixing in dry air. The cloud is growing in the centre and shrinking at the periphery simultaneously. It's like a forest fire that's spreading in one direction while burning out behind it. The net result is growth, but only because the growth rate exceeds the decay rate. The balance is precarious. Then something shifts. Maybe the updraft weakens because the surface heating decreases. A cloud passes over and shades the ground, cutting off the thermal energy source. Maybe the updraft runs out of buoyancy because it's mixed with too much dry air through entrainment. Maybe precipitation starts forming in the cloud core, and the weight of the water droplets creates a downdraft that competes with the updraft. Whatever the cause, the cloud stops growing. It reaches its maximum extent, its peak volume, and for a brief moment, maybe 2 or 3 minutes, it looks stable. This is the mature phase, the period when the cloud looks most impressive, most solid, most permanent. This is when you take the photo, but maturity is fleeting. The decay phase has already begun. The updraft continues to weaken. Entrainment accelerates, because the cloud is no longer being replenished with fresh moisture from below. The edges dissolve faster. The cloud base starts to rise as the lower portions evaporate. The cloud becomes less opaque, wispier, less defined. From the ground, it looks like the cloud is thinning out, losing its crisp edges, becoming more translucent. What you're watching is the slow-motion disintegration of the droplet population. Millions of droplets are evaporating back into vapor every second. The cloud is returning to the invisible reservoir it came from. Within 5 to 10 minutes of entering the decay phase, the cloud is essentially gone. Maybe there's a faint wisp left, a ghost of what it was, but even that dissipates quickly. The cloud has completed its life cycle. The water molecules that made it up are still in the atmosphere, still available to form the next cloud when the next updraft comes through. But this particular cloud, this specific collection of droplets organised in this specific shape, at this specific location, no longer exists. It lived for 20 minutes. It was never going to live longer. Larger clouds live longer, but not proportionally longer. A towering cumulus that reaches 4 or 5 kilometres in height might live for an hour or two before it either collapses into rain or dissipates through evaporation. A full-blown cumulonimbus thunderstorm can persist for several hours, but even then, you're not looking at one static cloud. You're looking at a cloud system where new cells are forming on one side while old cells are decaying on the other. The individual updraft cores within the storm each have lifetimes measured in tens of minutes. The storm persists because it's a conveyor belt of birth and death, constantly refreshing itself, but no single piece of it lasts very long. Stratiform clouds, the flat layered clouds that cover the entire sky on overcast days, can persist for many hours or even days, but that's because they're not isolated convective features. They're embedded in large-scale weather systems with sustained uplift over hundreds of kilometers. The cloud layer is being continuously maintained by synoptic-scale processes, not by individual updrafts. And even within that layer, individual droplets are cycling through formation, growth, and evaporation on timescales of minutes to hours. The cloud as a structure persists. The cloud as a collection of specific water molecules is constantly turning over. So when you look at that cumulus and think it's been there all afternoon, you're probably wrong. You're looking at the third or fourth or fifth cloud to occupy approximately that position. Each one looked similar enough to the previous one that you didn't notice the transition. Each one formed on the same thermal updraft that keeps triggering over the same warm patch of ground. They're reincarnations, not the same entity. The cloud you see now is not the cloud you saw 10 minutes ago, even if it looks identical. This is the central illusion, the one that ties everything together. Clouds look permanent because they occupy semi-permanent positions in semi-permanent weather patterns. But they're not permanent. They're processes disguised as objects. They're verbs pretending to be nouns. That motionless cloud is actually a life cycle running on fast-forward, birth and death happening while you watch. The whole drama playing out in less time than it takes you to eat lunch. And when the cloud finally vanishes, when you look up and realize it's gone, it didn't go anywhere. It just stopped being visible. The water is still there, invisible, waiting to be a cloud again when conditions permit. Nothing was lost. The cloud just changed forms, the way it's been changing forms constantly since the atmosphere first learned how to make clouds billions of years ago. You're watching a temporary agreement between physics and water, and the agreement expires quickly. Here's something you've probably never considered. Clouds talk to each other. Not with words, obviously, and not even with anything you'd recognize as communication in the way animals or humans communicate. But clouds influence each other's formation, trigger each other's growth, and can even kill each other through their interactions. They're part of a network, a system of feedback loops and cascading effects, and that isolated cumulus you're looking at is both sending and receiving signals that will determine whether its neighbours live or die. Let's start with the simplest form of cloud communication, the cold pool. Remember when we talked about precipitation forming inside clouds? When rain or ice finally gets heavy enough to overcome the updraft, it falls, and as it falls, it drags air down with it. This creates a downdraft, a column of descending air that spreads out when it hits the ground, like water from a faucet hitting a sink. That spreading air is cold, colder than the surrounding surface air, because it came from altitude where temperatures were lower, and because the evaporation of rain as it fell cooled it even further. So you've got this pool of cold, dense air spreading out from the base of the cloud, flowing along the ground, pushing the warm surface air up and out of the way. And here's where it gets interesting. That boundary between the cold pool and the warm air, called the gust front or the outflow boundary, is a lifting mechanism. The cold air acts like a wedge, sliding under the warm air and forcing it upward. If the warm air is moist and unstable, that forced lift can trigger new convection. New updrafts form along the gust front. New clouds begin to grow where the old cloud's cold pool pushes into the surrounding environment. You get a line of daughter clouds spawning downwind from the parent cloud, each one born from the death throes of the one before it. This is how squall lines form. One thunderstorm produces a cold pool. The cold pool's leading edge triggers new storms. Those new storms produce their own cold pools, which merge with the original one and expand the outflow boundary further. The boundary keeps propagating, keep lifting unstable air, keep triggering new convection. What started as one isolated cell becomes a line of storms marching across the landscape, each one feeding off the corpse of the previous generation. The clouds are communicating through fluid dynamics, passing along the message, "I'm dying, but here's some cold air to help you be born." There's another form of cloud interaction that's more subtle but equally important: moisture recycling. When a cloud evaporates, when all those droplets at the edges turn back into vapour, that moisture doesn't just disappear into the dry air and vanish, it humidifies the local environment. The air that was 60% relative humidity is now 70%, and that slightly more humid air is now more favourable for the next cloud to form. The condensation threshold is easier to reach. The next updraft doesn't have to work as hard to get air parcels to saturation. The dying cloud has left behind a legacy of moisture that makes the environment slightly more cloud-friendly. On larger scales, this moisture recycling becomes a feedback loop. A field of cumulus clouds, all evaporating at their edges, collectively humidifies the boundary layer, the lowest 1 or 2 kilometers of atmosphere where most weather happens. As the day progresses and more clouds form and dissolve, the average humidity increases. By late afternoon, the atmosphere might be saturated enough that clouds grow bigger, last longer, and produce precipitation more readily than they did in the morning. The morning clouds seeded the environment for the afternoon clouds. It's a relay race where each runner passes moisture to the next. Then there's the issue of cloud shadows. When a cloud blocks the sun, the ground beneath it stops heating. The surface cools, the air in contact with the surface cools, and any thermal updrafts that were building in that location shut down. If another cloud was starting to form in the shadow zone, its energy source just disappeared. The shadowed cloud never fully develops. It sputters and dissipates, strangled in infancy by its neighbour's shade. This is cloud murder essentially. One cloud kills another by cutting off its sunlight, but shadows can also organise convection in useful ways. If you have a field of scattered cumulus, their shadows create a patchwork of heated and shaded areas on the ground. The heated areas continue to produce updrafts. The shaded areas suppress them. Over time, the convection organises into the gaps between existing clouds, forming a quasi-irregular pattern. Clouds end up spaced at similar intervals because each cloud's shadow creates a dead zone around it, and new clouds can only form in the sunny gaps between shadows. From above, from a satellite perspective, this looks like the clouds have somehow agreed to maintain a polite distance from each other. They haven't. They're just responding to the same pattern of surface heating and shadowing that they collectively created. There's also gravity waves. When a cloud disturbs the atmosphere, when an updraft punches upward and displaces air, or when a collapsing cloud sends a downdraft slamming into the ground, it creates waves in the atmosphere, like ripples spreading from a stone dropped in water. These gravity waves propagate horizontally, carrying energy and momentum away from the cloud. When they encounter stable layers in the atmosphere, they can amplify, creating wave-like oscillations that move faster than the air itself. And when these waves pass through a region of moist air, they can trigger condensation at the wave crests, forming clouds in regular parallel bands. Those weird rows of clouds you sometimes see, perfectly aligned and evenly spaced. Those are often gravity waves from a distant storm, triggering cloud formation tens or even hundreds of kilometers away. The storm is communicating with the far field, sending out pulses that say, "I disturbed the atmosphere over here, and the effects are reaching you over there." And then there's the largest scale of cloud communication, the climate system itself. Clouds reflect sunlight back to space, cooling the planet, but they also trap infrared radiation emitted by the surface, warming the planet. Whether a cloud warms or cools depends on its altitude, its thickness, its droplet size, and about a dozen other factors. But the net effect is that clouds are in constant conversation with the Earth's energy budget. More clouds form when the surface warms, which reflects more sunlight, which cools the surface, which reduces cloud formation. It's a negative feedback loop. Except sometimes it's a positive feedback loop because more clouds trap more heat, which warms the surface, which evaporates more water, which makes more clouds. Climate scientists are still trying to fully understand which feedback dominates under which conditions, and it's one of the biggest uncertainties in climate modelling. So that motionless cloud isn't alone, it's part of a network. It's being influenced by the clouds that came before it, by the clouds currently surrounding it, and by the large-scale atmospheric state that all the clouds collectively help to create. And it's sending its own signals, through its cold pool, through its shadow, through its evaporating edges, through the gravity waves it generates, that will influence the clouds that come after. The cloud is a node in a web, a participant in a conversation that's been running continuously since the first clouds formed on early Earth. And you, standing there with your sore neck, see none of this. You just see a white puff that looks like it's doing nothing, but it's doing everything. This is the cloud feedback problem, and it's the single largest source of uncertainty in climate projections. Different climate models disagree most strongly not on how much greenhouse gases will warm the planet directly, but on how clouds will respond to that warming, and whether that response will magnify or reduce the initial warming. Some models predict that warming will produce more low clouds, which reflect more sunlight, which cools the planet, a negative feedback. Other models predict that warming will reduce low clouds and increase high clouds, which traps more heat than it reflects, a positive feedback. The difference between these scenarios is enormous. It's the difference between 2 degrees of warming by end of century and 5 degrees of warming. Recent observations and improved models are starting to converge on an answer, and it's not the comforting one. It looks like the dominant cloud feedback is positive. As the planet warms, low marine clouds, the stratocumulus decks that cover vast areas of subtropical oceans, thin out and break up more easily. These are the clouds that do the most cooling, because they're low and thick and cover huge areas. Losing them, even partially, reduces the planet's reflectivity. Meanwhile, high clouds don't decrease proportionally. They might even increase in some regions as atmospheric circulation patterns shift, so you're losing cooling while maintaining or even increasing trapping. Net result: clouds amplify warming. They're a positive feedback, not a thermostat. The seesaw is tipping. There's another wrinkle. Clouds don't just respond to climate. They help create weather patterns that then influence climate. The tropical Pacific, for example, has regions of persistent deep convection, where towering cumulonimbus clouds pump heat and moisture high into the atmosphere. These convective towers drive large-scale circulation patterns like the Hadley cells and the Walker circulation. Changes in where and how often these towers form can shift rainfall patterns across the entire Pacific basin, affecting everything from Australian droughts to South American floods. Clouds aren't just passengers in the climate system, they're drivers. And then there's the geological timescale. Go back 55 million years to the Paleocene-Eocene thermal maximum, when the planet warmed by 5 or 6 degrees over a few thousand years, rapid by geological standards. Proxy evidence suggests that cloud feedbacks during that event were strongly positive, amplifying the initial warming and keeping the planet hot for about 100,000 years. Go back further to snowball Earth events, when the entire planet froze over. The lack of open water meant fewer clouds forming, which meant less reflection in a system that was already icy and reflective, but also less trapping, and the math gets complicated quickly. But clouds were there, doing their dual role, influencing whether the planet could escape from the frozen state or stay locked in ice. So when you look at that drifting cumulus and think it's not doing much, remember, it's currently engaged in the single most important energy balance act on the planet. It's reflecting 50 watts of sunlight that would otherwise warm the surface. It's trapping 30 watts of infrared that would otherwise escape to space. It's part of a global ensemble of clouds that determines how much energy Earth retains and how fast the planet warms or cools. And the really humbling thing is that we're still not entirely sure whether clouds are going to save us from runaway warming by increasing their cooling effect, or doom us by decreasing it. The cloud doesn't know either. It's just doing what thermodynamics tells it to do, one droplet at a time, floating there in apparent stillness while participating in a planetary scale experiment with no control group. Then there's intentional cloud modification. Cloud seeding has been practiced for decades, where you inject silver iodide or other ice nuclei into clouds to trigger precipitation. Ski resorts do it to increase snowfall. Water-scarce regions do it hoping to squeeze more rain from passing storms. The effectiveness is hotly debated. Some studies show 10 to 15% increases in precipitation. Others show no statistically significant effect, but the practice continues. China famously seeded clouds extensively for the Beijing Olympics to ensure clear skies during the opening ceremony, by triggering rain upwind so clouds would rain out before reaching the city. It probably worked, though proving causation in a chaotic system is nearly impossible. More ambitious geoengineering schemes propose to brighten clouds deliberately. The idea: spray fine mist of seawater into marine stratocumulus clouds, providing extra condensation nuclei, making the clouds brighter and more reflective, cooling the planet. It's aerosol pollution but optimized and targeted. Sounds simple. In practice, it's fraught with unknowns. Would brighter clouds last longer, altering regional precipitation? Would you disrupt monsoons if you cool the wrong ocean region? What happens when you stop? Do you get rapid rebound warming? And who decides which regions get cooled, since making clouds brighter over one area might shift rainfall away from another? The physics might work. The politics are a nightmare, and we haven't even mentioned the clouds we create through land use change. When you clear a forest and replace it with farmland, you change the surface's albedo, its roughness, its moisture availability. All of these affect cloud formation. Deforested regions often produce fewer and different clouds than the forest they replaced because trees pump moisture into the atmosphere through transpiration, and because forest canopies create their own microclimates. The Amazon rainforest essentially makes its own weather, generating clouds that rain on the forest, which keeps the forest alive which generates more clouds. It's a feedback loop, and deforestation breaks it. Some climate models suggest that full Amazonian deforestation could reduce regional rainfall by 20 to 30%, and the cloud changes would be a major part of that shift. Urban heat islands, cities that are warmer than surrounding countryside because of concrete and asphalt absorbing heat, change convective patterns. Cities often trigger their own cumulus development downwind as the urban heat plume rises and condenses. Some cities get more afternoon thunderstorms than they would naturally. Others get smog-induced suppression of clouds because pollution particles are so numerous that droplets stay small and never grow large enough to precipitate. We've turned cities into cloud laboratories, running experiments we didn't design and can't easily control, so that still cloud, that motionless puff you've been contemplating, might not be entirely natural. Its droplets might have condensed onto sulfate nuclei from a coal plant 300 kilometers upwind. Its brightness might be enhanced by aerosols you contributed personally by driving your car this morning. Its existence at this specific altitude might have been influenced by the jet contrail that passed overhead an hour ago, altering the local humidity profile. We're in the clouds now, our fingerprints on every aspect of their formation and behaviour, and the cloud, oblivious, continues to drift and evaporate and scatter light, performing its role in the climate system with the indifference of pure physics, unaware that one of the species on the surface below has become powerful enough to change the rules it operates under. The still cloud contains our history, industrial, chemical, thermal, written in droplet-sized distributions and ice crystal habits, a ledger of human influence that we're only now learning to read. The cloud drifts nowhere because nowhere is the only honest description of a process that's happening everywhere simultaneously. It's not moving to somewhere else. It's constantly becoming something else while occupying roughly the same volume of space. Every second, it's a different collection of water molecules organised by the same physical principles into the same general shape. It's like the old philosophical question about the river. You can't step in the same river twice because it's not the same water. You can't look at the same cloud twice either. Not really, even if you never take your eyes off it. And in that paradox, in the tension between the apparent stillness and the actual frenzy of activity, there's something almost meditative. The cloud becomes a kind of koan, a puzzle that your rational mind can dissect and explain, but that still confounds your perceptual systems. You can know the cloud is changing and see it as unchanging at the same time. You can hold both truths simultaneously, the scientific understanding and the sensory illusion, and neither one invalidates the other. They coexist, like the cloud itself coexists with the clear air around it, like the visible water coexists with the invisible vapour, like the chaos coexists with the structure. So maybe the cloud drifting nowhere is exactly where it needs to be. Not moving, but also never still. Not permanent, but also always present in some form. Not simple, but appearing simple from a distance. It's a reminder that the world is more active, more dynamic, more interconnected than it appears. That stillness is often motion we're not equipped to perceive. That the peaceful surface hides complexity beyond imagination. And that sometimes, the most profound thing you can do is just stand there in a field, with your neck getting sore, looking at a cloud, knowing that you'll never see it the same way again, but that it will look exactly the same anyway, and that both of those things are equally true, and that's beautiful in a way that has nothing to do with beauty and everything to do with the stubborn, indifferent, magnificent persistence of physics doing what it does best, creating patterns out of chaos, structures out of randomness, clouds out of nothing, and making it all look effortless. The cloud drifts nowhere, which is to say, it drifts everywhere, which is to say, it doesn't drift at all. It just is, for as long as it is, which won't be long, but which is long enough. And you're here to witness it, to understand it, to carry that understanding into sleep where it might mix with dreams and become something else entirely. Some new pattern your brain creates from the raw material of droplets and turbulence and light. The cloud doesn't care. It's already beginning to dissolve, already becoming the next thing, already proving that stillness was always an illusion, and that the only constant is change, except the change is so continuous and so universal that it looks like stillness from where you're standing. And maybe, just maybe, that's the point. Your breathing has slowed now, matching the rhythm of gentle air currents, the ones you can't see but know are there, lifting and lowering and mixing everything together into something that looks simple but isn't. The cloud is fading from your thoughts the way clouds fade from the sky. Not gone, just diffused, spread out, mixed into everything else until you can't quite pin down where it ends and something else begins. Your eyelids are heavy. The physics becomes less sharp, the equations blur into impressions, and that's fine. That's exactly right. Because you don't need to hold on to every detail. You just need to remember that stillness is motion, that nothing is nowhere, that the cloud you saw was never really there, and was also more real than most things you'll touch today. Let the droplets fall. Let the ice crystals grow. Let the turbulence mix it all together into something you can't see but can finally fully understand. The cloud is doing what clouds do, and you, drifting towards sleep, are doing what you do, finding patterns, making meaning, resting in the space between knowing and not knowing, where the best questions live and the most honest answers sound like contradictions. The cloud drifts nowhere. You drift towards sleep. Neither of you is moving. Both of you are in constant motion, and somewhere between those two truths, in the space where paradoxes feel comfortable, and comfortable feels profound, you find exactly what you are looking for without ever having to look at all. Sweet dreams. The clouds will still be there tomorrow, doing everything while appearing to do nothing, and you'll look up and think they're peaceful, and you'll be right, and you'll also be completely, wonderfully, beautifully wrong.